Hello, my name is Catherine Fitzgerald. Throughout this presentation, I'll be taking you through some work I've been doing over the past 2 years throughout my master's degree. We've been aiming to synthesize and evaluate a set of F18 radiotracers which target a family of proteins called the BET protein family. So first, what are these BET proteins? So BET stands for bromodomain and extra-terminal, and these are a family of epigenetic reader proteins. Now, epigenetics relates to changes to DNA expression resulting from chemical modifications that are made to chromatin as opposed to actual changes to the DNA sequence. So there are 3 types of proteins which affect these changes. There are epigenetic writer proteins, which add chemical modifications, erasers, which remove these chemical modifications, and then readers, which recruit the transcriptional machinery to the chromatin to alter various DNA templated processes. Now, these BET proteins are a type of epigenetic reader protein, and what they do is they bind to acetylated lysine residues on histones. Now, within this family, there are 4 proteins. There's BRD2, 3, 4, and testis-specific BRDT. And these are all similar in that they all contain 2 tandem bromodomains. So these are highly conserved motifs which bind to these acetylated lysine residues on histones. Now, within this family, BRD4 is the most studied owing to its dysregulation in cancer. It's known to initiate and promote cancer and is also involved in a variety of inflammatory diseases as well. So in our lab, we're particularly interested in glioblastoma. So BRD4 mRNA overexpression is inversely correlated with overall survival in glioblastoma. And it's also been found that in patient-derived glioblastoma samples, BRD4 protein is overexpressed. So to go about designing a PET radiotracer, we thought using an already known BET inhibitor, a small molecule BET inhibitor would be a good place to start. So while there's a whole host of these small molecule BET inhibitors, this inhibitor in particular called trodebrezib caught our attention. So this is a BD2 selective reversible BET inhibitor produced by Bristol Myers Squibb, and it's currently in a few phase 2 clinical trials for the treatment of glioblastoma, astrocytoma, advanced solid tumors, as well as in combination therapy with temozolomide for the treatment of glioblastoma. So we thought that we could install a triazole moiety at the 6th position of this isoquinoline scaffold, thereby enabling us to use a prosthetic group methodology to get an F18 atom onto this scaffold towards the end of the synthesis. So using this click chemistry prosthetic group idea, we developed a series of 5 potential BET inhibitor-based radiotracers, which we called BiPET. So with these target compounds in mind, we then set about doing the synthesis to get these cold compounds. So the synthesis of these compounds was loosely based off of the sequence that was used to make trodebrezib, which we found in the patent literature. So by design, the last step of this reaction sequence is the copper catalyzed click reaction, which installs our F18 atom into this BET inhibitor. So this goes via a free alkyne, and here we break the molecule up into 2 fragments via Suzuki coupling. So we get our isoquinoline scaffold, to which we install the alkyne moiety via Sonogashira coupling, and then we also have our phenylsulfone moiety. And these can be accessed through these 2 commercially available materials. So going in the forward direction, we went about building this molecule by synthesizing these 2 fragments separately and then bringing them together in the convergent synthesis. So starting off with the isoquinoline fragment of the molecule, we started from this material and we methylated it first, and then we brominated at the enamide-like 4 position. Now we reasoned that the 4 position was sufficiently electron-rich relative to the 6th position to confer regioselectivity for the 6th position in the palladium cross-coupling Sonogashira reaction. So indeed, we found that we did get this regioselectivity and we obtained the desired TMS-protected alkyne and 69% yield. So that got us our isoquinoline fragment. Now moving to the phenylsulfone fragment, we started off here. So for the methyl derivative, we purchased this sulfone, and then for the ethyl derivative, we accessed this via formicaptophenol as outlined in the retrosynthesis. So first we did a monobromination ortho to the phenol, and then we alkylated this phenol under basic conditions to give us our 5 requisite aryl bromide precursors. So then we subjected these to a Majora borylation cross-coupling reaction. Now, initially we attempted to isolate the pinacol boronate ester directly. However, we found that this was unstable on silica. So we opted to trap this with diethanolamine, and that gave us these nice air-sensitive solid diethanolamine complexes to work with. Now, the next step in the reaction is to marry these 2 fragments together by Suzuki coupling. So for this, we employed standard Suzuki coupling conditions. Now, for this cross-coupling reaction, it did work for the first 3 entries in this table. However, for the bottom 2 entries, we did only see decomposition. Now, we didn't investigate this any further, but this decomposition is probably owing to instability brought about by new modes of reactivity that open up at the alpha position of the ethyl sulfone when you go from the methyl to the ethyl sulfone. So moving forward, we ditched these 2 bottom compounds and we decided to persevere with the top 3 compounds going forward. So once we had the TMS protected alkynes in hand, subsequent deprotection under basic conditions gave us the desired free alkynes. So in the final step, we did the click chemistry reaction. So we reacted the free alkyne with 2-fluoroethyl-azide under copper catalysis and basic conditions with the polytriazole ligand TBTA as a promoter of this click reaction. So with these cold compounds in hand, we characterized them via mass spec X-ray crystallography, and we did do some 2D NMR on these compounds to verify that we had synthesized these target compounds. So next we decided to characterize the binding of these compounds to the target protein. So this was done by a structural biologist at Bio21, Dr. Michael Gorman. So what he did is after we had obtained 2 plasmids from AdGene for both bromodomains of BRD4, he kindly expressed these in E. coli and then purified them by FPLC to give us 50 milligrams each of these bromodomains. And then before moving into the protein crystallography, we did some thermal stability assays. So in this assay, we're looking at a change in melting temperature on addition of a ligand that binds to the protein, and a significant shift in melting temperature is indicative of that binding. So for instance, shown here is that shift in melting temperature that we saw when we added trodebrezib to the first bromodomain of BRD4. And this melting point change of 11.8 is quite a big melting point change for this assay. So we found that promising and we persevered with the co-crystallizations. So with both bromodomains in hand, we did some co-crystallizations with trodebrezib bipet 1 and bipet 2. Unfortunately, we were unsuccessful in getting crystal structures of the second bromodomain. However, we were successful with the first bromodomain. So you can see these crystal structures here. These are all solved to less than 1.5 angstrom, which is excellent resolution. So we got some really good data. And as you can see, these inhibitors are all binding into this acetyl-lysine binding site. They're anchored into this cleft via the formation of a hydrogen bond with the asparagine 140 residue, and they're also held there by various hydrophobic interactions. Now, another thing we did is we did some molecular docking studies with AutoDoc-Vena to see how well we could predict the binding modes of these ligands in silico. And I've shown these dock structures here in blue. So you can see that the program is predicting the binding of these ligands quite well. So having validated or investigated the binding of these compounds to the target protein, we then moved on to the radiochemistry portion of this project. So in essence, the synthesis is identical, except now we're working with F18 2-fluoroethyl-azide, and we're also working with an automated synthesis module. So we were able to radiosynthesize F18 bipet 1, 2, and 3 in 23, 39, and 63% decay-corrected yield, respectively. We made these in greater than 99% radiochemical purity, so no further purification was required. We also calculated the log P values for each of these compounds via the shake flask method. So we found that they were 1.3, 1.9, and 1.2. So these are all within the desired range for our bioavailability as outlined by Lipinski's rules. We also did some preliminary metabolism studies in S9 rat liver fractions, and we found that after 2 hours of incubation in these liver fractions at 37 degrees, F18 by PET3 retained over 99% RCP. So that bodes well for our in vivo studies. So next we did some in vitro screening to select suitable cancer models, glioblastoma models, for our in vivo study. So first we screened a panel of 4 glioblastoma cell lines. We had U87MG, GL261, GBM1 and GBM3, which were patient-derived samples. And we screened these with our parental compound trotabresib. So what we found was that U87 was a weak responder and GL261 responded well and gave us nice curves. So we then proceeded to screen our compounds in these 2 cell lines. So as you can see, for each of our bipet compounds, we saw that they had higher IC50 values in U87 and lower IC50 values in GL261, as was the case for trotabresib. And of note in GL261 is that bipet 2 is performing the best out of our compounds. So we nominated that as a lead compound. However, given we get differentiation for all of these compounds, bipet 1, 2, and 3 are all potential radiotracers that we will progress forward to in vivo studies. So finally, we did some target validation with F18 by PET2 in an adherent cell uptake assay. So we administered 1 microcurie of F18 by PET2 to 2,000 cells per well of U87 and GL261. And also in half of the wells, we pre-administered with 10 micromolar trotabresib to see if we could block the target in these cells. So 3 things came out of this assay. We saw that the less sensitive cell line had higher uptake than the more sensitive cell line, indicating that the target expression might be higher in U87MG. So we're currently investigating that with some Western blot studies. Secondly, we found that the target was blockable. So after administration of the 10 micromolar of trotabresib, we did get that significant decrease in uptake, which bodes well for our in vivo imaging study. And finally, we saw that the uptake kinetics were rather rapid. So after 1 minute, the uptake didn't really increase, and it kind of increased slightly after 1 hour. So the next step of this project is a pilot in vivo imaging study, which is going ahead in the next 2 weeks or so. So we have ethics approval for 2 mice for each of our candidates. So we're going to subcutaneously xenograft these mice with U87MG cells, and then we'll image with each bipet radiotracer doing 2-hour dynamic PET MRI scans. So thanks for listening to the talk. I just want to thank my supervisors, Professor Jonathan White, Dr. Ingrid Bervenik, Dr. Uwe Ackerman, and Professor Andrew Scott, and all of my collaborators and mentors. Thank you.